Moore's law is dead. Moore's law isn't dead. Moore's law is being replaced with something else. Moore's law will go on for another 100 years. So on and so on. All this talk about Moore can get pretty tiring, and now we have here yet another thing about Moore's law. We talk about it all the time, but what has Moore and his law really been about? In this video, we look at the story and long-lasting impact of Moore's law. But first, let me talk about the Asianometry Patreon. Early access members get to see new videos and selected references for those videos before they're released to the public. It helps support the videos, and I appreciate every pledge. Thanks, and on with the show. When Gordon Moore wrote his famous 1965 article, the integrated circuit, or IC, was itself just 5 years old. Dr. Moore had not yet even founded Intel. He was then still the director of research and development at Fairchild Semiconductor. The article is less of a rigorous scientific analysis and more of a marketing white paper. At the time, Fairchild's ICs were not selling well outside of the government, so Moore was going around trying to persuade engineers to incorporate ICs into their products. The 1965 article's intention was to convince the reader that ICs were the cheapest way to make smaller electronic devices and systems. What was initially dubbed as Moore's plot was just one part of that argument. In a section titled Cost and Curves, he notes that in 1965, the most economical IC, meaning to have the lowest per component cost, had about 50 components. The term component was then defined as a function or device including diodes and resistors, in other words, more than just transistors. He writes, the complexity for minimum component costs has increased at a rate of roughly a factor of 2 per year. He also produced the now famous plot, showing the component counts of Fairchild's IC chips over the past 4 years. Extending out the plot, Moore predicted that in 1970, an economical IC will have about 1,000 components, and then 10 years later, or 1975, an IC would have 65,000 components. I want to note here that the math was wrong. If the baseline was 50 components in 1965 and we double each year, then by 1970 we should have 1,600 components, 50 times 2 to the 5th power, not 1,000. And by 1975, an IC should have 51,200 components, 50 times 2 to the 10th power, not 65,000. I do admit that he said that the rate was roughly 2 per year, but that roughly is doing some serious heavy lifting. Anyway, Moore's core point is that the cost of producing a chip is dependent on the cost of printing and etching an IC design onto a wafer. He then argues that this cost is not correlated to how many components are actually on that design. So, if the ICs get more complex, complexity being defined by component counts, but the costs stay the same, then the cost per component trends down. The 1965 article was widely read and debated. Moore's prediction that denser or more complex ICs would get cheaper on a per-component basis was controversial. The generally accepted wisdom back then was that system miniaturization always added costs rather than cut them. This presumption was for very real reasons. For instance, several research managers at Bell Labs argued that an increasingly complex IC was far more likely to have one or more of its components not work. This would, of course, ruin the whole chip, so in fact, the yield rates for increasingly complicated chips would approach 0%, making them unimaginably more expensive. Yet others pointed out the graph's small sample size, as well as the issue that the only data points it used for were from Fairchild Semiconductors, classic Reddit and Hacker News stuff. Regardless of the feedback, Gordon Moore and his comrades used Moore's plot to guide the technology roadmap first at Fairchild and then Intel. Moore pushed his R&D lab people to double chip complexity by a factor of 2 each year, knowing that more complex chips are more profitable. 3 new technologies introduced in the 1960s allowed this to happen. The first was new lithography equipment, like the contact printer, to improve the resolution at which we can mass print chip designs. Equipment advances are one of the core drivers of innovation throughout semiconductor history. The second major technology was a new gate structure, the silicon gate MOS transistor. These are the IC's basic electronic component. There are billions on a single die, switching on and off. A transistor is made up of a gate sitting on top of a channel, connecting a source and a drain. The gate allows or disallows a current to move along the channel from the source to the drain. What was special about the silicon gate MOS transistor was the fact it used polysilicon for its gate. This gate performed far better than the previously used aluminum gate because it could bear higher temperatures without melting. The silicon gate was discovered by 4 companies, including Fairchild Semiconductor, at about the same time in the mid-1960s. But it was Intel who first bet the farm on it in the late 1960s, a bold technical choice that paid off in letting them cram together 3 to 5 times more gates than ever before. The third technology came out of the design world. Intel's first breakthrough products using silicon gate technology were memory chips, SRAM and DRAM. These memories can be more easily integrated into systems and perform far better than the magnet-based ferrite core memories that had been used up until then. Remember those from the Wong Labs video? Anyway, the memory chip's fundamental building block is the memory cell, which stores 1 bit. Throughout the late 1960s and early 1970s, designers achieved shrinkage by slimming down the number of transistors in that memory cell's design. The first memory cells used 6 transistors each. Intel's first DRAM IC, the Intel 1103, first introduced in 1970, had 3 transistors per memory cell. Then, a 1-transistor memory cell, first developed by Robert Dennard in 1966. This 1-transistor memory cell would eventually enter the market in the mid-1970s with the 64 kilobit generation. These 3 advances made a component doubling each year technically possible. But as it turned out, a 1-year process node cadence was too fast for Intel's customers, system designers like IBM. They wanted new chips every 3 to 4 years, rather than 1. This was reinforced by an American tax depreciation law that specified a 6-year depreciation cycle for computer buyers. A new memory generation hitting the market each year was just too frequent. So Intel introduced a new generation of memories with a 4x increase in density every 3 years. Intel can sell these leading-edge products at the start at a good price. Once competitors like TI catch up, Intel can move up the next step on Moore's plot. The older product thereafter rapidly declines in price. This wine vintage model, as some call it, is well known. They ported this model from memory to microprocessors soon after the category's invention in 1971. Moore's plot worked because it was predictable. At any one time, Intel might not always have the absolute best microprocessor compared to those from Zilog or Motorola. But they could sell customers on that product's future. You could point to the plot and tell the customers that the microprocessor in front of them was going to get better down the line. That predictability helped customers gain confidence in the product. As Intel ascended to become America's most prominent and profitable semiconductor company, Moore's plot became more accepted by some of its peers. TI, AMD, and Motorola adopted it in some form for their technology roadmaps too. In 1975, 10 years after the original article, Gordon Moore gave a follow-up speech. By then, Dr. Moore had succeeded Robert Noyce as Intel's CEO, bringing a great deal of publicity to his plot. At around this time, people, Caltech professor Carver Mead perhaps his most fervent adherent, started referring to the plot as a law. Also by this time, the benefits of silicon gate technology had started to peter out. Intel's engineers were having difficulties pushing out more complex ICs. The smaller the silicon gates got, the less control the gates had over the flow of electrons moving from the source to the drain. This causes contamination. Still, Moore felt that his 1965 prediction had worked out. In that 1975 speech, Moore cited the existence of an IC with 65,000 components, a 16 kilobit charge-coupled device or CCD memory. But in recognition of the growing technical challenges of cramming more components onto an IC, Moore announced the revising of his law's cadence down from a doubling every year to every 2 years, starting in 1980. Technically, Moore's 1965 prediction was right, the best kind of right, but that CCD memory turned out to be commercially uncompetitive. The chip would be far better known for its eventual use in solid-state imaging. The most advanced mainstream memory technology at the time, the 16 kilobit DRAM, was at least a year away from commercialization. Even then, this memory IC had less than half of the 65,000 component prediction. Reflecting on that 1975 speech, Morse seemed a bit surprised that so many people cared about his changing of the goalposts. I don't think anybody was planning their business around it, probably because I was basking in the glow of the first prediction being right. I don't think anyone was paying any attention to it. So, Moore's original 10-year extrapolation turned out to be quite wrong. Yet, Moore's law didn't get tossed into the trash like that 2-day-old white rice in the fridge. Instead, the industry modified it to make delicious fried rice. The 1970s-style DRAM chip differs from its microprocessor friends in that it is made up of regular repetitive memory cells. To get a more sophisticated memory chip, as in to have more capacity, you have to stuff together more and more memory cells into the same space. Logic chips, on the other hand, were seen as more of a design challenge than a production challenge, at least back then. As a result, in the 1970s, when people talked about Moore's law, they were more often referring to memory rather than logic chips. To them, making memory chips was the best pure expression of raw production ability. This production ability matters, since this memory was a commodity, the first to market with the next generation reaped the most profits. Japan's rapid catch-up to the American semiconductor industry was built on continuing that cadence of quadrupling memory bit capacity every 3 years. They were first to the crucial 64 kilobit generation, leapfrogging the Americans, which took almost 2 years to catch up. And thanks to the strict control of manufacturing processes, Japanese yields soared. The cost of making a Japanese memory IC plunged, undercutting American products. When the DRAM market crashed multiple times throughout the first half of the 1980s, Japan's lower cost structure, among other things, allowed them to survive the market turmoil while many American companies couldn't. Part of the reason why Japan surged ahead in the early 1980s was that Intel and the rest of the Americans fell behind in Moore's law. Measurements of Intel's microprocessor densities find a weird flatness in the early 1980s, a period of time when Japan and others surged ahead. This 3-year period is because of the company's struggles transitioning to a new generation of lithography equipment. In his 1975 speech, Moore cited 3 significant factors contributing to continued increasing complexity. The first one was to increase the size of the die. The second was called technical cleverness. In other words, using computer automation tools to lay out designs that can make better use of the chip die canvas. The third thing, and the one most relevant today, was the decreased line dimension, the depth, width, and density at which we can etch circuit designs onto silicon. Improvements in lithography equipment, encompassing machines that do exposure, resist processing, and etch, have largely driven the upper limits of complexity for semiconductors since the late 1970s. When those lithography advancements stall, it filters down the chain. In the early 1980s, Intel needed to produce their own 64 kilobit DRAM chip. The standard lithography tool back then was the projection aligner. These tools projected a chip design across a whole wafer. However, the 64 kilobit needed more resolution than the aligner could provide. So Intel had to move on to the newly introduced stepper, a device that moved across the wafer step by step, ergo the name. They struggled with it. Intel's first yields in 1982 came in at 40%. It took another 2 to 3 years, 1985 basically, to bring those production yields up to 75%. Intel's previous generation 16 kilobit DRAM came out in 1979, so it means a 5 to 6 year gap between new node generations. This lithography delay contributed to Intel exiting the commodity memory business entirely, reorienting the company towards their growing microprocessor business. At the same time, the company recommitted itself to manufacturing. In 1983, Dr. Moore instructed his colleagues to accelerate their manufacturing capability to match that of the Japanese, 4 times every 3 years, or doubling every 18 months. That October, in a talk given at the DataQuest Semiconductor Industry Conference, Moore publicly redefined his law once more, revising the complexity doubling cadence to the aforementioned 18 months. I did a video detailing this before, but throughout the late 1980s, Intel and the Americans recommitted to manufacturing, raising their yields enough to erode the Japanese advantage. When Japan's semiconductor industry fell into overcapacity in their core commodity DRAM market, it triggered a massive crash. The industry consolidated, and Japan lost its mojo to the Koreans. Intel sidestepped this memory disaster with its pivot to microprocessors. This, as well as its revival in manufacturing, returned the company to prominence. To them, this was thanks to renewed adherence to Moore's Law. In the early 1990s, the U.S. federal government began a slow retreat from direct involvement in technology policy, something started during the first Bush administration and continued by Clinton. This included the sunsetting of the National Advisory Committee for Semiconductors. The U.S. government set this up in 1988 to figure out a long-term roadmap to keep America at least one node generation ahead of the Japanese by 2000. This plan was called Microtech 2000, and with the government now stepping back, the Semiconductor Industry Association, or SIA, was asked to fill the void, take over the Microtech plan, and run it as an ongoing living document. Moore jumped in. In the fall of 1991, he convinced the other heads of the semiconductor industry to use Moore's Law and its concept of ever-doubling complexity as the basis of a new, unified national roadmap. Together, the companies created an R&D cartel directing the industry's entire future. Since achieving increasing complexity requires massive resources that only large companies have, it favored established incumbents. This new national roadmap, called the National Technology Roadmap for Semiconductors, received substantial buy-in from the government. Moore's Law became the deciding factor for hundreds of millions of dollars in federal investments like those from DARPA. Every academic research proposal was judged on whether or not it helped continue the complexity pace of Moore's Law. During this period of time, America's entire semiconductor industry achieved convergence. In the popular video game Dead Space, convergence happens when the necromorphs gather together at a marker, triggering the release of incredible bursts of energy. You, as the video game protagonist Isaac Clarke, have to stop this convergence event. A similar thing happened with America's semiconductor industry in the 1990s. This convergence event standardized all the materials, equipment, and processes, drastically cutting down on cost and releasing incredible bursts of productivity. In 1995, Gordon Moore gave a speech at an SIA dinner, reflecting on 3 decades of Moore's Law. In that speech, Moore claimed to be surprised as anyone that the law's tenets, albeit so revised, continued to hold. He said that all exponentials had to end, but when? He had given up on trying to predict when that might be. That ending was still far away, for Intel in 1995 was about to come into a burst of lithography equipment improvements. Deep ultraviolet, or DUV excimer lasers soon entered the market. These sophisticated lasers replaced the old eye-line lamps companies used for lithography, unlocking a vast new green field for lithographic improvements. In 1999, the industry started using 248nm krypton fluoride lasers for their leading-edge process node at the time, 180 nanometers. 2 years later, in 2001, 193nm argon fluoride lasers, I will always call them ARF, entered the market. These are substantially similar to their 248nm predecessors. These enabled Intel to rapidly commercialize new technology nodes at 3-year intervals, progressively reducing their transistor's smallest dimension 30% each time. Intel's adherence to Moore's Law caused semiconductors to get better and cheaper at the same time. Prices for a particular microprocessor, introduced from 1995 to 2000, would rapidly fall somewhere from 50 to 70% 1 year after its introduction. It was a great time for IT vendors. They automatically received better and cheaper performance every generation without needing any change to their products. The introduction of 193nm lasers allowed Intel to hit its Moore's Law cadence from 2001 to 2003. But those lasers were unsuitable for the next node step coming in 2003, the 70nm node. and unfortunately, the next generation of lithography technology Intel had selected, EUV, was not ready. Furthermore, generations of shrinkage had weakened the gate's control over the flow of electrons so much so to cause power consumption issues. Thus, in 2004, Intel shifted to multi-core processors, abruptly ending the streak. It took users by surprise, forcing them to rewrite software at great expense to be parallelized. The introduction of 193 immersion lithography in 2006 allowed Intel to unlock new gains in semiconductor manufacturing. With EUV still seemingly years away, Intel moved ahead, feeling that they could do without it. They were, of course, wrong. Right now, the company is looking to recover their node step speed with a rapid adoption of EUV and high-NA EUV. Hitting the right lithography technology remains critical to achieving the next leading-edge node and enabling further progress in computing power. So, as you can see, Moore's Law was not only never a law, it was never even remotely predictive of anything from the very start. That original concept back in 1965 was nothing more than a vaguely defined chart covering a single 4-year span in what was then a very young industry, one of those up and to the right charts they put into VC pitch decks. That original concept died a long time ago. So, what is Moore's Law now? It is a mythology, a story that maintains the culture of an entire industry, much like the scriptures of a religion. And like with any sensible mythology, the story has been reinterpreted and redefined over the years to fit the audience of the time. Regardless, the ambitious concept of ever-increasing complexity remains. You might be thinking to yourself now, well, gosh, we don't need things to be faster. I've been using the same phone and PC for years now. Why do we need this effort? I reject this form of technological nihilism. The average consumer might not see it anymore in their phones or gaming rigs, but other industries are still craving more computing power. Our economy and society still have many complicated technical problems, and throwing more computing at those problems has consistently been the best way to solve them. A recent very interesting paper out of a team at MIT Computer Science and AI Lab, led by Neil Thompson, looked at the impact Moore's Law has had on 3 economically significant areas: weather prediction, protein folding, and oil exploration. Each of these multi-billion-dollar industries have greatly benefited from increased computing power. For instance, take the weather. From 1956 to 2017, the amount of compute power used by the NOAA has increased by 1 trillion times, compounding at 48.2% a year. Over that same time period, the error rate in temperature predictions has declined from 5.8 degrees in 1972 to just 3 degrees in 2017. You can attribute up to 94% of this improved accuracy solely to the additional compute power, with improved algorithms coming up a distant second. Getting even better results will require yet more computing power. Were it not for the complexity advancements provided by Moore's Law, such improvements would not be economically feasible. And to me, that is why Moore's Law matters. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.